did this with left Riemann sum. Well, first with a right Riemann sum, then with a left Riemann sum. We said that the right Riemann sum, because this is a parabola that opens down, since it's a decreasing function, and he said that a right Riemann sum would be an underestimate of what the true area under the curve was, and left Riemann sum would be an overestimate of what the actual area under the curve was. So we went through with the right Riemann sum, and we said, imagine there was n rectangles. We wrote it out. We wrote down what that would look like in terms of a formula, and then we took the limit as n goes to infinity, and saying that right Riemann sum is going to be an underestimate. We got 18. Then we came back with the left Riemann sum, and we broke it down and wrote out n rectangles, took the limit as n goes to infinity, knowing that the left Riemann sum would be greater than or equal to the actual area under the curve, and it became also 18. So that told us then that the actual area under the curve, which was between 18 and 18, must have been 18. It must actually be right. So the bottom line from that is that if you are going to take the limit as the number of rectangles goes to infinity, it really doesn't matter how you set up your rectangle. Left Riemann sum, right Riemann sum, anything you want. Once you take the limit as n goes to infinity, whatever differences they may have go away, and you're going to get the true area under the curve, which we're calling that definite integral. So we did that with an interval going from 0 to 3, and we used those formulas along the way as part of what we were doing when we took the limit as n goes to infinity. So that was pretty long and involved, but now I'm going to add yet another complication. So instead of starting the interval at 0, we're going to start it somewhere else, and as we'll see, that makes it significantly more complicated, and we'll try to fight our way through all that. Okay, so that's our goal here. So it's a more complicated example of what we talked about last time. So this is more finding the area using what we call a limit process. So we'll choose as our function, let's say we'll do f of x is going to be, we'll say just plain x squared, and we're going to make our interval go from, let's say, from 1 to 3. Okay, so I'll draw a picture. You don't have to have the picture, but I think it kind of helps just see what's going on here. So our x squared we're familiar with, that's going to be our parabola that opens up. We're interested in the interval, so what we're actually evaluating, I should say, is going to be this integral from 1 to 3 of x squared dx. Since our x squared function is always non-negative, then this integral is truly going to be the area between the curve and the x-axis. So there's 1, 2, 3. So we're looking at, use your imagination a little bit. That parabola may take some fun bends. So we're essentially looking for this area in here. And we're going to start out by dividing this into n rectangles and trying to figure out how to make a formula for that work. And then we're going to take the limit as n goes to infinity, and then it'll go from being an approximation to the area under the curve to the actual area under the curve. And it'll be an evaluation for this definite integral. So as we talked about last time, this is our third way of evaluating the integral. One is making an area argument, like we talked about. You know, if you had something like a semicircle that was radius 3. So that function would be the square root of 9 minus x squared. We could say that integral from -3 to 3 of the square root of 9 minus x squared. We could use an area argument and say, oh, we know the area of a circle is pi r squared, so the area of a semicircle is going to be 1/2 pi r squared, and so we could get that's going to be 4.5 pi. And so we could say this integral is equal to 4.5 pi. The second way we learned is with our calculator doing FN integrate. And so that's our second option, and now this is our third. This is one that's gonna kind of be in the category of like when we first started talking about derivatives, and we said its definition is the limit as h goes to 0 of f of x plus h minus fx all over h. You're like, oh my gosh, if we have to do that forever, this calculus is gonna be long and tedious, but pretty soon we went to some shortcuts. This is gonna be in that same category. So this is an understanding of what's happening kind of conceptually and behind the scenes, but we are going to get our fourth way in not too long, which will be way more efficient than this. So we're not going to do it this way for long. Okay, so here we are, and we're going to, because we're going to take eventually the limit as n goes to infinity, it doesn't really matter how we set up our rectangle, left Riemann sum, right Riemann sum, midpoint. So it's way easier to conceptualize doing right rectangles. So that's what we're gonna do. So we're gonna imagine now that we're gonna come over here, and I'm not worried really about the width of those rectangles, except that they're gonna be uniform width. So we're gonna make these all be the same width. And this is just more for conceptualization, that we can see this. We're gonna get these rectangles and we're gonna do n of them. So we are going to say that this integral from 1 to 3 of x squared dx is approximately equal to first, and we're going to get the sum of these n rectangles. So each of these, A1, A2, A3 represents the area of one of those rectangles. Area of the first rectangle, the second, out to the nth one. Now, we're going to make these uniform width. So our delta x that is the width of each one of those rectangles, is the same for each rectangle, uniform width. And it's going to be always the b minus a over n. So the a is our lower limit, 1. The b is the upper limit, 3. So our delta x is going to be 3 minus 1 over n, or that's going to be 2 over n. That's the width of each of those rectangles. Okay. So that first rectangle, so I'm going to write this in detail here. We're going to take f of, and I'm going to talk about what that value is going to be. It's going to be the right side of that subintegral, the right side of that rectangle. And then it's going to be times the delta x, which is that width. And then we'll get our second rectangle. So we're going to figure out what's the x value. How are we going to name that x value that we're going to plug into the function to get the height of the second rectangle. And that's going to be times that delta x. And we're going to do that all the way out to the nth one. So our nth rectangle is going to have a height of f of x of n and a width of delta x. Now, this is the first major obstacle here, is what are we going to name that? So we want to plug into our function this x value right here. That is the right side of that subintegral. And so the question is, how are we going to call, what are we going to call that? And so the suggestion I'm going to make is 1 delta x, one width of that rectangle, added to 1, the lower limit. So it's going to be 1 plus that delta x. That's the x value that we're going to plug into the function. You with me there? 1 plus that width. And that width of that rectangle is 2 over n. So the x value that we're gonna plug in for that first rectangle, we're gonna take f of 1 plus 2 over n. And for counting purposes, this may seem weird, but the reasons for it will become clear in not too long. I'm gonna call that 1 plus 2 over n times 1. So it's one rectangle width to the right of 1, because then I'm gonna keep adding more and more of those as we work our way to the nth rectangle. So that's gonna be f of 1 plus 2 over n times 1. That's gonna be the height of that first rectangle. The width of that rectangle is gonna be delta x, which we said is gonna be 2 over n. So that's gonna be times 2 over n. There's now the area of that first rectangle. Plus, now we're gonna get the area of the second rectangle. So again, the hardest part to conceptualize is we're gonna plug in for the x value. Now we are at, now the second one, our x value is gonna be the 1 that was our lower limit of integration, plus now we are 2 of those rectangle widths to the right of 1. 2 delta x's, 2 of those 2 over n's. So we're gonna call that 1 plus 2 over n times 2. That's how we're gonna count that. And then times delta x is the width, which is again gonna be 2 over n. Let's do one more, and then we're gonna run out to the nth one. So now at our third rectangle, you can kind of see the pattern. We're gonna get f of, what will that be?
1 plus 2 over n.
Times 3. And then times that 2 over n. So first rectangle is 1, 2 over n to the right, second one is 2 over n's to the right, and the third one is 3 2 over n's. Then we're gonna run out to the nth one. So our nth rectangle, now we know that the right rectangle is gonna end up being at 3, but we're not gonna write it as f of 3, we're gonna write it in the same counting scheme that we started here. So we're gonna call that f of
1 plus 2n times n
exactly.
times 2n.
Exactly, okay? So even though that's f of 3, we're gonna write it in the form f of 1 plus 2 over n times n. Okay, now, little algebra, all of these n rectangles have a common factor of that delta x, which in our case is the 2 over n. So I'm gonna factor all of those out. So there they are. All of those get pulled out. Okay, now is where it starts to get even uglier. We're gonna evaluate f of 1 plus 2 over n times 1. Well, our function is x squared. So that means we're gonna plug in 1 plus 2 over n times 1 into that function squared. So it's gonna be 1 plus 2 over n times 1 squared. That's our first rectangle. Height plus, and we pulled out the 2 over n. Now we're gonna plug in 1 plus 2 over n times 2. So that's gonna be 1 plus 2 over n times 2 squared.
Why is it squared?
Because our function, we're plugging into f, and our function is the x squared
okay.
function.
Okay, I got it.
So whatever that might be. Okay, third one, what's it gonna look like?
1 plus 2 over n times 3 squared.
Nice. Okay, running it out to that nth one. What's that?
1 plus 2 over n times n squared.
Very good, and bracket. Okay, now we'll see how good our algebra skills really are. So remember we said the shortcut for squaring something out, when you have a plus b squared, that's a plus b times a plus b, which is gonna give us the first term squared, and we're gonna get 2 of the product of those terms, twice the middle term, or twice the product, we say, and then we're gonna get that second term squared. So the shortcut is we get the first one squared, twice the product, plus the second one squared. We're gonna use that now. Okay, so the first one squared is this 1 squared. And I'm just gonna leave it as 1. Twice the product means we're gonna take the 1 times the 2 over n times 1, and then times a 2. So that's 1 times 2 over n times 2, because it's twice the product. So, well, the 1, that doesn't really do anything. The 2, I'm gonna bring it here with the 2 over n and call that 4 over n. Now, it doesn't also multiply the 1, because we don't distribute over multiplication. So it's, all these are being multiplied, but I'm gonna bring the 2 and the 2 over n together, but I'm gonna leave that times 1 next to it. So that's gonna be 4 over n, and for counting purposes, I'm gonna leave that as a 1. We okay so far? Plus, now we get the second one squared. So the 2 over n times 1 squared. When you have 2 things raised to a power, 2 things that are multiplying and being raised to a power, each of those gets raised to the power. So the 2 over n, that fraction, and we also know that when you take a fraction to a power, the numerator and denominator both get raised to that power. So the 2 over n squared is going to become 4 over n squared. The 1 is also going to be squared, and I know 1 squared is 1, but for counting purposes, we're going to call that 1 squared. All of that, and I'm going to just put it in parentheses so we can see it proved. All of this came from our f of that first term, that first place, that first height of our first rectangle. Okay, now, plus, the second we're gonna do the same thing again. We get the first one squared, that's 1. We get twice the product, which is now gonna be what?
4 over 8.
4, just the product now, so we're gonna get 4 over n times 2. Is that what you said? Okay, I misheard that. 4 over n times 2. And then plus the second term squared, which is gonna be
4 over n squared times 2 squared.
times 2 squared, exactly. Okay, let's go to our third one, and that's gonna be, first one squared is gonna be, twice the product is gonna be
4 over n times 3.
good, and the second one squared is gonna be
4 over n squared times 3 squared.
nice. And bringing it all the way out to the nth one. And the nth one is the 1 plus 4 over n now times n plus the 4 over n squared times an n squared and bracket. Okay, so these parentheses, now remember these are n rectangles. We have, there's 1, 2, 3, all the way up to the nth one. All of those have a 1 plus inside them. So I'm going to ignore the other stuff for a minute, but I'm just going to add all of those together. 1 plus 1 plus 1 plus 1 n times all adds up to be how much?
And
N. 1 n. So I'm going to write that, I'm going to bring them all together, and that's going to go in the first term. That's all the ones added up together. Now, I'm going to ignore the squared terms, but we're just going to direct our attention to those middle terms, all the ones that have 4 over n times something. So we have a 4 over n times 1, a 4 over n plus a 4 over n times 2, plus a 4 over n times 3, plus all the way out to 4 over n times n. Those terms all have a common factor of,
4 over n.
so I'm going to factor that out, and that will leave behind, after we pull out that 4 over n, what's going to be left behind is,
And
well, it's going to be 1 plus 2 plus 3 all the way out to n. So it's the sum of all of those. Does that make sense? Okay, now ignoring everything else, but directing our attention to those square terms. Those things that have 4 over n squared times some number squared. They all have a common factor of 4 over n squared, which is gonna leave behind, when we factored out of those terms, we're gonna get 1 squared plus the 2 squared plus 3 squared all the way out to the n squared. And I'll go back to a bracket in the white. Okay, this is progress. Now, when we look at these sum of the 1 out to n, 1 plus 2 plus 3, that is that formula that we see on the front of that Larson worksheet, the sum of the i's from 1 to n. That's what we have right here, 1 plus 2 plus 3 all the way out to n. That could be written in summation notation this way, and it's telling us we have a formula for that really all of those are gonna add up to be that n times n plus 1 all over 2. So I'm gonna replace all of this stuff by that formula. You with me? Now, on the other one, when you see this 1 squared plus 2 squared all the way out to n squared, that in summation notation is our sum I going from 1 to n of the I squareds. That's the 1 squared plus 2 squared all the way out to there. That has a formula. So I'm going to replace all of this by its sum, which in that formula is n times n plus 1 times 2n plus 1 all over 6. And you don't have to memorize the formulas, I'll give those to you. Okay, so now what does this look like? Well, this looks now like 2 over n. There's our n. That was really the first formula. I didn't really use the formula. We just said 1 plus 1 plus 1 n times is going to be n. That's the sum of c, where the c is 1 n times. Now then this part is going to be plus, we have the 4 over n, and now all of this is being replaced by that formula, n times n plus 1 all over 2. Okay to there? Plus, we've got this 4 over n squared times, and all these sum of the squares are being replaced by its formula, n times n plus 1 times 2n plus 1 all over 6. So we've now kind of distilled this down to kind of a formula. If we wanted to approximate this area under the curve, which is the same thing as approximating this definite integral, using a Riemann sum, and we wanted to say, now we can pick how many rectangles do you want? Do you want to approximate this with 10 rectangles? Well, plug in a 10 for all of those ends, grab your calculator, and you'll get an approximation. And you say, I want a better approximation, so I use more rectangles. That'd be 100. Plug in 100 for all those ends, throw it on your calculator. That's going to be a better approximation. We're not settling for an approximation, we want the exact value. So what we're going to do is take the limit as n goes to infinity. So we are going to take the limit as n goes to infinity of, now, what I'm going to write down here, we're going to distribute this. So there are, inside these brackets, there are 3 terms separated by the plus signs. This is 1 term, that's a 2nd term, and that's a 3rd term. So when we distribute, this 2 over n is going to hit each of those. So when we take the 2 over n times the n's will cancel, and we're just going to get 2. Now, these are being multiplied, so we take that 2 over n and we can let it hit that 4 over n, We don't also distribute it to the rest of this, because we don't distribute over a multiplication. When we hit the 2 over n with the 4 over n, it'll carry it with it as we simplify this multiplication in a minute. So we're gonna call that 8 over n squared. Okay, so that's a plus 8 over n squared, which is still going to multiply at n times n plus 1 all over 2 in a moment, as we go to take the limit as n goes to infinity. Now, same story with that third term. That 2 over n is gonna hit this 4 over n squared, and that will carry it with it as we continue the multiplication in a moment. So the 2 times the 4 is 8, the n over the n squared is n cubed, and the rest of this stuff is patiently waiting its turn. Okay. Now, here's where the arithmetic becomes way easier, because we're gonna take the limit as n goes to infinity. If we were trying to make this a formula and we were gonna actually plug in a finite number for n, we'd have to be very careful about how we multiply this all out. So if you do multiply this out, which I have no intention of doing, if we multiplied this all out, you know, we would get the highest power of n that would emerge here would be an n cubed. There'd be another term that had n squared, another one with n in it, and it'd be a mess. But because we're gonna take the limit as n goes to infinity, the only thing that matters in both of these expressions is what is the highest power of n in its coefficient. So in this term, we're gonna get an n cubed term. We would get, if we multiplied it out, an n squared term, but that, compared to n cubed, as n goes to infinity, it's not gonna matter, so we're not even gonna worry about it. Same thing with the n term. And this, the highest power that's gonna emerge is an n squared, and the other term we don't really care about, so we're not gonna sweat it. So as we look at each of these terms that have n's in them, we're just picking out the highest power of n and its coefficient, and that's it. Okay, so this is now going to be the limit as n goes to infinity. Now, the first term doesn't have any n's in it, so it's unaffected by what n does, it's staying 2. Now, in the second term, we're just picking out, as we multiply everything in the numerator, the highest power of n and its coefficient, and that's gonna be what?
8n squared.
8n squared. And at the bottom, we're gonna get 2n squared. So I'm gonna write it right now as 8n squared over 2n squared. And we'll come back to that and clean it up in a minute. Now, the third term, we got all this junk. If we pick out the highest power of n and its coefficient in the numerator, what is that going to become?
16n cubed.
See it? 16n cubed? So that's gonna be a 16n cubed, and in the denominator, we're gonna get
6n cubed.
6n cubed. Now, the rest of this stuff, as n goes to infinity, it's not gonna contribute, it's not gonna matter, it's gonna be dominated, it'll be dwarfed by these higher powers of n. Now, each of these we can simplify, and we can say, well, you know, as n gets huge, n squared gets big, but these 2n squareds are gonna both get big at the same rate. So when you plug in 1,000 for n and squared, it's the same as that 1,000 squared there. Plug in 1,000,000 and squared, it's the same as that 1,000,000 squared. Those aren't gonna matter, they're gonna cancel each other out. The 8 divided by 2 is gonna be just 4. Same story with the cubes, they're gonna cancel each other out. 16 over 6 we can reduce to 8/3. Now you can go mixed number, improper fraction, either way. I think maybe mixed number might be a little easier. That's 2 2/3, right? So the 2 plus 4 plus 2 2/3 is going to be
8
8 2/3. That is our integral from 1 to 3 of x squared dx. Now you, if you have your calculator, you can confirm that by doing FN integrate. And maybe we should do that. We haven't done that in a while. Might be a fun one to do on your graph, actually. Cause you see, as you go from 1 to 3, you'll see it shade. I don't know any way to do it, cause you'll see it shade this part of it that's in between 2 and 3, and it'll leave that part from 0 to 1 to be blank. Let's go, y1 equals x squared. And then for a window, let's go maybe like x min 0, x max 5. So you'll see some blank spaces on either side. And for a y min, let's go -1. And for a y max, let's see, when we plug in 3, y max, let's go 10. So let's go 0 to 5 on the x and -1 to 10 on the y. I think that'll give us kind of a nice little window into that. Remember how to do that, or you need some help? To do the shading, so you have to do it off the graphing menu. So you have it graphed first. Okay, now go second trace to the calculate menu. And then somewhere down there, you'll see an integral sign. I don't remember what number it is. 7, see it? Okay, so hit 7 and enter. Then it's gonna ask you for the lower limit. And that's gonna be the 1. That's our lower limit of integration. And hit enter. And that's gonna ask you for the upper limit. And then you'll get 3. Isn't that kind of slick? Hit 3 and then enter, and then watch that screen, because it'll just shade in. It's like that Riemann sum that's filling in underneath there. And is it getting, since we got 82/3, so if we round to 3 decimal places, would we get 8.667? Does that look right?
Yep.
Okay, so we're great. Now, what the calculator is doing, crazily enough, it's doing a bunch of rectangles. And it's taking rectangles that are 1/10,000th in width. And so it's computing each of those, and it's doing like what we were doing here, but actually plugging in numbers, where the delta x is 1/10,000. And it's gonna be accurate to within 3 decimal places, which is what we need most of the time. The safer way on the test is to use the one off of the math menu. Questions on that? All right, so 13 minutes. Can you do one in 13 minutes? That's what I like to hear. Okay, let's see if we can do one. We'll attempt one anyway. So you can find a spot on the board. And we are going to, let's see, let's go, do it, it'll be manageable. That's good. There's no business.
My asses are so bad.
What's that?
My asses are so bad.
No, that's,
It's like low level abs.
I trained you for it, yeah.
Oh, boy, these just get so big in a hurry. It's gonna get big, 1 to 4. Getting started is the hard part. One of the hard parts. What's our delta x gonna be on this one?
3 over.
Nice. So we are gonna plug in, the first value of x that we're gonna plug in is gonna be
1 plus 3 over n?
Good, 1 plus 3 over n, and let's say times 1, because we're gonna need that counter. 1 plus 3 over n times 1, times our width, which is gonna be another 3 over n. Okay? You just do 2 of them and then we can run out to nth one. Hopefully. Remember, you got an extra plus 1 in here on your function that we didn't have before. So when you plug that in, you're gonna plug this 1 plus 3 over n times 1 in for the x. That's gonna get squared, and then you still have another plus 1.
Alright.
So we're plugging in 1 plus 3
For each of those, you're gonna get that first one squared twice the product, plus second one squared, plus 1, because of the x squared plus 1. So looking okay for your first term?
Yeah. Wait. What? Oh, never mind.
That make sense?
Yeah.
So when you go to collect terms, you're gonna get each of those rectangles is gonna have a 1 from the first one squared twice the product plus second one squared, but it's also gonna have a plus 1 from the x squared plus 1 part. So each rectangle is gonna contribute 2. So there's n of them. So when you add those 2's n times, you're gonna get a total of 2n. There's all those ones added up. Then the terms that are getting multiplied by 1, 2, 3 out to n all have a common factor of 6 over n. So you're gonna factor that out of those. And likewise, you're gonna factor a 9 over n squared out of all those square terms. check your work after you pass a certain step and make sure that you're right before you go on to the next one, so you don't have to go back and.
This is gonna do the formula.
How are you doing, Darren? How are you doing? Great. So we're gonna distribute the 3 over n, and we're gonna take the limit as n goes to infinity. Before we do that limit as n goes to infinity, we're gonna do our kind of fuzzy math. We're gonna